Hi guys, welcome to 6.5 part 2. So we did the exploration, which should have given you an idea of the shapes of different polar graphs and what each component, the coefficient, and whether it's cosine or sine, and what n does as far as affecting the graph of a polar graph. And so today we're going to synthesize all that information, just make sure that it's all nice and neat for you in one place and you have the names of everything. And then we're going to graph two by hand with quality by filling out our theta tables. So first off, we did these, any polar graph that was in this category over here. And if n was 1, then that would be like a one-petaled rose, but turns out that's not actually a one-petaled rose, that's a circle. So while it's not necessarily wrong to call it a one-petaled rose, we would want to call it by the better name, which is the more specific name, which is a circle. But if n was greater than 1, then this is called a rose. These are all in the rose category. And we had said that if n was even, then there are 2 n petals. If n is odd, there are n petals. We had also said that in both of these cases, that A was the petal length, which coincidentally, like in the case of a circle, then A would be the diameter of the circle. You can also just be safe thinking of it as petal length. And then the last thing that we hadn't talked about was whether it was a cosine or a sine. So if it's a sine graph, then that means that it is centered on the y-axis. And if it's cosine, it's on the x-axis. If it's a positive cosine, then it's on the positive side of the x-axis. And if it's a negative cosine, it's on the negative side of the x-axis for the circles. For the roses, we talked about that if it was a cosine graph, I know I don't have an argument here, but if it was a cosine rose, that the first petal was on the positive side of the x-axis. But if it was a sine rose of some sort, then the first petal was at 90 divided by n, or pi over 2 divided by n, depending on whether you're in degrees or radians. So that is pretty much synthesizes that whole category, which you can actually count as 2 categories because that takes care of circles and roses. And then we moved on to this other category with the one that has 2 terms, the r equals a plus b cos n theta and r equals a plus b sine n theta. And actually you don't have to worry about an n in this case. You just have to worry about the a and the b. And so these are all in a category that is called limaçons, and the word is French. Actually, the same word that means snail, I believe, in French. So I know it looks like a C, but it's a C with a little hook on the end of it. Don't know what that's called. And it means it sounds like an S. So it's not limacons. Please do not pronounce this limacons. I'm so glad that if you're going to, that I don't have to hear you pronounce it that way. That this is limaçons. And because it's French, like you're not really going to put that N on the N, it just gets a tiny little bit of an N sound. So I hope that you're all practicing saying that right now. That's the broad category for it. However, depending on what A and B are, they have more specific names. So you actually have to learn the more specific names because just saying that it's a limaçon is not going to count. Like it's not going to be good enough. So here are the categories. The first one and the easiest one is called a cardioid, and that's when A equals B. When A equals B, as in the case of 2 plus 2 sine theta, r equals 2 plus 2 sine theta, then we end up with this little shape that if you turned it upside down, it would look like a heart. And the prefix for anything related with the heart is cardi or cardio. So this is a cardioid. and that's when A equals B. When A is less than B, as in the case of the fourth one that we have over here, then what happens is that's the one that is going to go in on itself, because 1 plus 2 is 3, but 1 minus 2 is -1, and a radius of -1 means that that's what's kicking it back in on top of itself. And so that one is called a limousin with inner loop. And so that's when A is less than B. So those two are both pretty easy. The next one is called a dimpled limousin because it looks like a little dimple. The dimpled limousin you're going to get, in the case of the r equals 3 plus 2 sine theta, you're going to get when the ratio of A to B is bigger than 1, but less than 2. So that means that A divided by B is bigger than 1, so which means A is bigger than B. But if the ratio is less than 2, it means that A is not double B. So in the case of 3 plus 2 sine theta, 3 is more than 2, but 3 is not double 2. So that's what means it's going to be a dimpled limousin, which is this shape that you'll see right here, that's just kind of a dimple. It's not a hard cusp like a cardioid. So I can show you a little bit. The cardioid is going to, like if we zoomed in on that, it would look like a cusp. Whereas the dimpled one, it kind of just comes in and then out like a dimple. That one is not super centered because I'm using a stylus, but there you go. You get what I mean there. So that one is the dimpled limousin. And then the one that we haven't done yet, the last one, is just called a convex limousin, and that's when the ratio of A to B is 2 or more. So with A divided by B, if A is double B or more than double B, as in the equation r equals 4 plus 2 sine theta, then what happens is 4 plus 2 is 6 at the top, 4 minus 2 is 2 at the bottom, and then what happens at this minimum is that it's kind of just flat, like it's a circle with a flat side, for lack of a better way to describe that to you. So you do need to know those 4 names and how we get them. Remember that if it's cosine, then it's centered on the x-axis, and if it's sine, it's centered on the y-axis. And the maximums are always going to occur at A plus the absolute value of B, and the minimums are always going to occur at A minus the absolute value of B. Which hopefully you saw from your homework last night. So we want to give like quality by hand graphs of some of these. So for instance, r equals 5 sine theta is the first one out of the 2 that we're going to do. And we know that this is a circle. And we know that because n is 1, and we know that the petal length or the diameter would be 5. And we know that this is going to be on the positive y-axis because it's a positive sign. So we know that it's going to look like that if that was a circle. There you go. And so because we know that that's what it's going to look like, that will help us, because then if we start messing up our graph, then we'll know that we did something wrong. So I'm going to pick values of theta that are on the unit circle. So I'm going to pick 0. We're going to go in degrees here just because I think that you're more comfortable with it. You should be able to do either one. So then we're going to have 30 degrees, 60 degrees. Oh, now wait, we'll put 45 in there. We may as well put 45 in there as well. So 45 degrees, 60 degrees, 90 degrees. Let's see how that gets us, like if that gets us enough or not. So then when theta is 0 degrees, then r would equal 5 times the sine of 0 degrees. But the sine of 0 degrees is 0, because you know that from your unit circle. And so this would equal 0. So I'd have a radius of 0 at an angle of 0, which would give me that first dot right at 30 degrees, then this would be 5 times the sine of 30 degrees. The sine of 30 degrees is 1/2, and 5 times 1/2 is 2.5. So I would find the 30-degree mark, and I would go out 2.5 at the 30-degree mark and put a little dot there. Next, 5 times the sine of 45 would be 5 times root 2 over 2. We're going to use the approximations that we used on the 4.4 notes, that root 2 is approximately 1.4 and root 3 is approximately 1.7. So root 2 divided by 2 would be 0.7, and 5 times 0.7 would be 3.5. So at 45 degrees, I'm going to go 1, 2, 3.5 and stick a dot right there. At 60 degrees, then this is going to be 5 times the sine of 60 degrees. The sine of 60 is root 3 over 2. So if root 3 is approximately 1.7, then root 3 divided by 2 would be approximately 0.85. And then let's go ahead and type that in, see what we get. That would be 4.25 approximately. Right, and these are approximately equal signs. So then I get 60 degrees and 1, 2, 3, 4.25. I'll put that there. 15 and 75, while they're on our polar graph paper, are not unit circle values that I care about. So we're skipping those. And then when I get to 90, then I get 5 times the sine of 90, but the sine of 90 degrees is 1, so that is 5 exactly. 5. Once we have that, I don't really need to continue values on the other side, because I know that the property of sine, that the values in quadrant 2 are going to mirror the values in quadrant 1 for the sine function. So because it's a sine graph, it's going to have y-axis symmetry. That means if I go to 120, it would be back at the 4.25. If I go to 135, it would be back at 3.5. If I go to 150 degrees, it would be back at 2.5. And then at 180 degrees, I would be back to 0. So it turns out if I connect these dots, I get the circle that I thought I was going to get all along, but I can see a couple different things here. First off, I can see better quality. Like I can see higher points on this, which is nice, like higher quality, more points, more specific points. And then I can also tell that I can actually get this whole circle just by going from 0 to 180 degrees. That will actually give me the whole circle. So then what actually happens when you're going from 180 degrees to 360 degrees? Turns out that because the sine in quadrant 3 is negative, then you would be in the third quadrant, but have a negative value. And so it turns out it kicks back to quadrant 1 and it just repeats itself. It just loops on top of itself. So if you go from 0 to 2 pi, you actually have 2 iterations of the complete circle. Just one more interesting note here. This also you can parallel with the graph of y equals 5 sine x, and this is actually super convenient and might help you out a little bit. So if I think about the graph of y equals 5 sine x, and if this is 5 and negative 5, I know that the graph of 5 sine x would look like this. It would start on the principal axis going up, and then it has a period of 2 pi units. And so instead of y, I actually have r, so this could be the r axis, and instead of x, I have theta, so this is the theta axis. And so what happens is I can see from this graph that I go from 0 to 5 and back to 0 in pi units, which corresponds with the fact that I'm going from 0 to 5 and back to 0 in pi units, and then I get there in 180 degrees. Okay, so that's one of the two. So for the second one, I want you to try some of this on your own. However, I'm going to help you out a little bit here. We're looking at r equals -4 times the cosine of 5 theta. So the negative is going to make it a little bit trickier, and then the 5 theta makes it trickier as well as far as the actual coming up with nice points. So I know that this should be a rose. It should have 5 petals because n is 5. The petal length should be 4 because a is 4. And then the negative is what's going to kick it to the opposite side so that the first petal would actually be on the negative x-axis. So there's 1, 2, 3, 4, 5. This is a bad sketch, but a sketch nonetheless of what it should approximately look like. I know that if there are 5 petals, 360 divided by 5 is 72. So each petal should be 72 degrees apart from the next petal, or 2 pi-5. So I know a lot about it before I start. However, when we do the same thing as we did before, 5 theta is what I'm taking the cosine of. So 5 theta is what we actually need to be using the values of the unit circle for. So I'm going to go ahead and say then theta would be 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And then we'll see what happens after that. So if 5 theta is 0 degrees, then I'm taking -4 times the cosine of 0. So I get -4, and that would be this point right there, because 0 would be the positive x-axis, but I'm going to kick it to the negative side because it's a negative radius. At 30 degrees, I'd have -4 times the cosine of 30 degrees, which would be -2 root 3, which would be approximately -3.4. So again, use the approximations I gave you on the last page because the whole goal is that we're getting a nice, lovely picture without using a calculator. So I'm going to find the angle 30 degrees, which is right here, but I'm going to then go to the opposite side of that, the negative side of that right here, and I'm going to put my dot at -3.4. So 1, 2, 3.4 would be about right there. And so it's a little bit tricky when the radius is negative. You have to be careful about that. Okay, next, ooh, sorry, man, I even messed myself up because I forgot to fill out this other column. Don't do what I just did. Could have gotten 2 points on the board. So here, 0 is 0 degrees, no problem. But here, 30 degrees is not actually this angle. 30 degrees is actually 5 theta, which means that theta is actually a 6-degree angle right there. So I want to be at -3.4 at 6 degrees. And so if this is a 15-degree increment, then that would be like super close. So there you go. The next one, this would be -4 times the cosine of 45 degrees. So that would be -2 root 2, which would be approximately -2.8. But that's not actually 45 degrees because 45 is 5 theta. So this is at 9 degrees, which again, this each angle that's marked here is 15. So I want to be at -2.8 at 9 degrees or so. So that would be right here. You can see that we are getting this petal, but it's just a lot of work. And so we can talk about how we can make this process go a lot faster. One way to make the process go a lot faster is to only pick the values of cosine or sine that will give you the nice neat numbers. Don't pick the values that will have a root 3 or a root 2 in them if you're looking at a rose. Not a circle, you should do all of them, but with a rose, we could have really skipped these because they don't have nice neat cosine values. Of course, you can have them in. It's not wrong to have them in. It's great extra quality, but it's a lot of extra work. So let's say I just did 60 degrees. Well, then that would be -4 times the cosine of 60 degrees, which would equal -2. And if 60 degrees is 5 theta, then theta would be 12 degrees. So at 12 degrees, I'm going to be at -2, which would be about right there. And then at 90, we know that the cosine of 90 is 0. And so -4 times the cosine of 90 degrees would be 0. And then I'm right here. And then the angle doesn't actually matter. But 90 divided by 5 would be 18 degrees. So what this has done is it's given me this piece, which is half of one petal. However, once we have half of one petal, we actually don't need to continue. We can, especially if we want to see like where it's going to go next in the pattern, because it doesn't actually go in the petals consecutively if you've watched your calculator graph it. So this does tell me that it hits this halfway point of -2, 12 degrees away from where the petal tip was. So that's going to help. I'm just going to use that one to do the rest of them. So I know that if I go 12 degrees on this side, that's going to be where it hits the, that's where it hits 2, and that'll help me out with that one. If they're 72 degrees apart, then I'm going to go ahead and go 72 degrees here. So this would be 15, 30, 45, 60, 75. So 72 would be about right there. And then again, if I go 12 degrees each way from where that petal tip is, then that's where it's going to hit a radius of 2. So 72 minus 12 degrees would be 60. And 72 plus 12 degrees would be 84. Right? And so again, I'm not considering standard position angle when I say 72 degrees. I just meant 72 from where my first petal was. So then there you go. We've got that one. Then we know that the one down here is going to be the same. So I'm going to go 72 degrees away from this first petal. So 15, 30, 45, 60, 72 would be about right there. And 72 minus 12 takes me back to 60. And 72 plus 12 takes me to the 84 degrees away. And I've got, oh, sorry. And there you go, I've got those dots. Then I'm going to go another 72 degrees away. So if this was, so I'm aiming for 144 total, right? So from the first petal. So this is 90 degrees, and then 105 degrees, and then 120 degrees, and then 135 degrees. So if I'm going for 144 degrees away from the first petal, then that would land me right there. And then 144 minus 12 is 122. Sorry, 144 minus 12 is 132, which is right here on the other side of that one. And 144 plus 12 would be 156, which would be over about right there. And there you go, got that petal in. And then last but not least, we can see that it's going to have the symmetry here. So we can just go ahead and put those in on the other side like so, because we know that they have the symmetry. So was this a big pain? Yes, especially when we knew that it looked like that before we even started. Seems like a pain. However, which graph has higher quality? Certainly the one where I went and bothered to get all those marks has higher quality. I can also mark, just for my sake, I can mark that these are 72 degrees apart, so that would be the angle of rotation. And then my math lab may also ask you about the symmetry of these. So we would say this has x-axis symmetry because you could flip it on the x-axis. We would also say it has rotational symmetry of 72 degrees. You would always give the smallest angle of rotation. Every single picture has rotational symmetry of 360 degrees, right? If I go like that, then that was 360 degrees. And then look, I'm in the same spot that I was before. That doesn't count as symmetry. So don't bother to say rotational 360. You would pick the smallest angle of rotation. And so this would have x-axis and rotational symmetry of 72 degrees. Also try not to make the petal tip super pointy, like that one is not high quality. Like try and make them rounded at the ends, just to, try to increase the quality. And so I hope that this helps you out. You have 2 that you're going to graph on your homework on the back side of that worksheet. And then also on the back side, I've given you a couple graphs, and you're going to go backwards and find the equations on that. So I hope that you have fun with that. And I will bid you adieu for now.